In order to understand what the displacement thickness is, let us quickly draw another schematic of the boundary layer. So like I said, the edge of the boundary layer, we define it as the location where the velocity almost reaches the free stream velocity. And we know that it will actually never reach the free stream velocity no matter how far you go, but at 0.99 times the u infinity, wherever the velocity becomes 0.99 u infinity, we can say that that is the edge of the boundary layer. But a more appropriate way of defining the edge of the boundary layer is by means of the displacement thickness. So let us look at how we can rigorously define an appropriate thickness. Okay, so the incoming flow was looking something like this. Okay, so the incoming flow was looking something like this. Everything was u infinity, while at any other axial location, okay, the flow encounters a retardation inside the boundary layer, while outside the boundary layer again it is u infinity. So what is the deficit of the volume flux? So the deficit,
Hello, Moto.
pardon me. So the deficit of the flux is equal to integral 0 to infinity u infinity minus u dy. Okay, so this is the deficit in the flux. So the question is, in order to match this deficit in the flux, what would be an equivalent displacement with this free stream velocity to account for this? So the equivalent displacement to account for this deficit will be equal to that displacement thickness multiplied by u infinity. Okay, so this is the formal definition of delta star. So displacement thickness is represented by delta star. So it is the displacement required in the free stream in order to match the same volume flux. In fact, if I draw this schematic, it will be clearer. So this is the boundary layer. This is the incoming free stream velocity. So if I were to imagine this as the control volume, so u infinity comes in, but only u, so u infinity times this height. So suppose let me call this height as h. So u infinity into h comes in integral 0, not h, delta. So I am taking the same height. Okay, so this will be u infinity times delta, and this will be integral u dy times delta, u dy going from 0 to delta. So if I want to have this incoming flux over at this cross section as well, I must change the shape of the control volume to something like this. I must change the shape of the control volume to something like this, so that at this cross section I have an additional plus some u infinity times delta star. So this is the delta star. So now if I match the incoming flux in this on this face and the outgoing flux on this face, u infinity times delta is equal to integral 0 to delta u dy plus u infinity times delta star. And this implies u infinity times delta star is equal to, so this becomes integral u infinity minus u dy going from 0 to delta, and we know that beyond the boundary layer u infinity minus u will go to 0. Hence this delta can be replaced by infinity. Hence we obtain the rigorous definition of the momentum of the displacement thickness. The displacement thickness is essentially a measure of the nature of the variation of the u velocity with y. So depending on this integral, you will obtain different displacement thicknesses. But it should be clear what the physical interpretation is. It is that how much distance should this streamline be displaced by into the free stream to obtain the same volume flux. Now, going by the same analogy, we have something called as the momentum thickness. And the momentum thickness is, I mean, sometimes they call it theta, sometimes they call it delta double star. I will call it delta double star. It doesn't matter what you call it. What's important is the concept. So it is the loss of momentum in the boundary layer. Okay, so it is sort of the loss of momentum due to the retardation in the boundary layer in comparison to the momentum that is coming in. Okay, so we can write it as, so the incipient momentum. What is the incipient momentum? It is u infinity square. Okay, actually let us write this in terms of u infinity and delta star. So u infinity square delta double star is the compensation momentum. So it is much like the compensation volume flow rate. This was the compensation flux. Okay, and that is equal to the difference in the momentum. So what is the difference in the momentum inside the boundary layer? So going from 0 to delta, at the at this particular point you are carrying a momentum of rho u, not rho, so it is simply u infinity, while inside the boundary layer you are carrying a momentum of u square. Okay, it is defined as this. So it's as if this u flux, okay, the flux inside, if it were to carry, so this is the advection part, and if that advection part were to carry a free stream velocity, if that advection part to carry a free stream velocity, then this was the opportunity momentum, if you may. Okay, it's like the opportunity cost. This is what momentum that flux would have carried, but instead of carrying that flux, it is carrying a flux equal to u square. So u square is basically comprised of u times u, and one of these u is the advection u, and the other u is the velocity u, the momentum component u. Okay, so this is what the loss in momentum because of the velocity retardation looks like, and this can be simplified as, so all this is by definition. Okay, 0 to delta, you can easily define anything you want, but redefinition of various terms are not going to change any physics, but it's just gonna lead us to a varying degree of simplification. That is why we are striving to this. So this can be written as u times u infinity minus u dy. And once again, because of this particular form, this 0 to delta integral can be written as 0 to infinity, because this will tend to 0 beyond y equal to delta. So therefore we have two definitions. The first definition is delta star, and delta star was this. So if we divide everything by u infinity, this term becomes 1. In fact, let me write it down. U infinity delta star is equal to integral u infinity minus u dy going from 0 to infinity, and this implies u infinity is delta star is equal to integral 0 to infinity 1 minus u upon u infinity, and the momentum thickness delta double star. So if you just divide everything by u infinity square, so this becomes 0 to infinity u by u infinity times 1 minus u by u infinity. So let me pull this equation once again. So the thing about this is you don't have to rely on that 0.99 u and all that to get an estimate. Okay, so this would become integral 0 to u infinity del x. So the del x I can take out of the integral because it's a 0 to infinity thing. So del x of integral 0 to infinity u times u infinity minus u dy. So we've just seen that that is equal to u infinity square times delta double star. And what about this? And because we are integrating it all, this whole thing will become function of x only. We are integrating it in y direction, so there will be no y dependency after integration, so this will become ddx. So what about this term? This term, it will become du infinity dx times, so this is equal to u infinity times delta star. So if I can write it in this form, so u infinity du infinity dx times delta star. So all this simplification, we are able to write down the wall shear stress. So wall shear stress in terms of the momentum thickness and displacement thickness. But as you can imagine, in order to estimate delta double star and delta star, what you need is an estimate of this profile. We need an estimate for this profile. Now we've drawn several times various profiles. Okay, we've drawn several profiles. So one such profile, I mean something very simplified, u by u infinity can be a parabola. Okay, up until a certain point, and then 1 as we move away from the boundary layer thickness. But all this we'll see in the next class. But for now, let us quickly see one more small thing. Uh, what about the free stream? So if we have a constant free stream, a uniform free stream, in the uniform free stream, because the plate is also flat, the plate is also flat, so du infinity dx will be equal to 0. Okay, if plate is flat and the flow is uniform, incipient flow is uniform, so all this equation will boil down to this. Because u infinity is a constant, it can come out of the integral as well. In fact, Okay, so depending on the nature of the delta star star or the momentum thickness, we can get an estimate of the wall shear stress. So that wraps it for today. We've looked at a lot of things. We've looked at the simplifications of the governing equations to obtain the Prandtl equation. Then we have looked at the momentum integral method to reduce the differential equations, to integrate them over control volumes, and to find out a very simple expression for the wall shear stress in terms of two newly defined parameters. One is the displacement thickness and the other is the momentum thickness. So in the next class, we'll continue with this approach. We'll assume various profiles to fit uh, the the boundary layer conditions, and once we have various profiles to fit those, we can find out various expressions for the wall shear stress. We'll have a brief outline of the Blasius method for solving all this. It's a self-similar solution, and we'll look at some concepts of flow separation and all this behind a circular cylinder. So it's a goodbye from me. Bye.